dimensions and tolerancing. Okay, when we say dimensions and tolerances, we are talking about fits and sizes, and how do you really specify those when you many machine components. So we have something called the nominal size, which is the mean or the average size. Then we have the limits, which would be, in this case, the maximum or the minimum size. Third is tolerance. So this would be the difference between the maximum and the minimum size. Okay, then we have within tolerancing, we have two types of tolerances. One is called the bilateral tolerance. Where we specify sort of plus and minus. So this is basically the variation around the nominal dimension. So an example of bilateral tolerance is, let's say that we have a shaft and it is 1.05 inches. That's the nominal size, but could be plus or minus 0.001. So it could be plus or minus 0.001 inches. Okay, so that is a bilateral tolerance. It doesn't have to be that the upper limit is the same as the lower limit. They could actually be different. Then similarly, we have unilateral tolerance. An example of that would be 1.05 plus 0.001, which means that it could be 0 or plus 0.001 over the nominal. There is no lower limit. The lower limit in this case is understood to be 0. Okay, and then there is when you have two mating parts like a shaft and a hole, you also have to worry about clearances. So there is known as interference fit, where the shaft doesn't go in the hole, and the clearance fit where the shaft does go in the hole. And that's kind of obvious that you want to usually have as small as clearance as possible so that it can snugly fit, the shaft can snugly fit into the hole. Okay, so with that, let's do a problem on limits. And this is again posted on the handouts. Yes, let's read the question. Okay, a shoulder screw contains 3 hollow right circular cylindrical parts on the screw before a nut is tightened against the shoulder. To sustain the function, the gap W must equal or exceed 0.003 inch. The parts in the assembly depicted in the figure have dimensions and tolerances as follows. So here we're given bilateral tolerances for A, B, C, and D. And you can see A is this, B is here, C is here, D is here. All parts except the part with the dimension D are supplied by the vendor. The part containing the dimension D is made in-house. Estimate the mean and tolerance on the gap W. Okay. So what's happening here is there is these different different components A, B, C, and D, and they have their own tolerances. And when you buy these from the supplier, they are guaranteed to be within this dimensions. So if you're not careful about their dimensions, then you will have a case where this W could either be, uh, in this case there's a gap, but if B and C and D are such that they are bigger than the cumulative size than A, then they would actually not fit into this part. So there would be a problem there. So it's important to check the dimensions for W, and that's what we're trying to do. So when we asked to find the mean and tolerance of gap W, so we need to find the nominal size, that's the mean, okay? And then what we'll do is we'll denote the deviation. So we'll use this notation. We'll say that A bar is the mean, it's 1.75, and then the deviation is, in this case, it's 0.003. So in this case, you can see that the tolerances are bilateral and they're the same. So I don't really need to use a different notation for delta A. Otherwise, I would have put delta max and delta min, but in this case, I can just use delta A because it's the same dimensions, plus or minus. So I'll use this notation and so on for other B, C, and D. Okay, so let's find the mean of W, and that's simple as just taking the means of the individual parts. Now you observe that A is over here, and in order to find W, you need to subtract B, C, and D from A, right? Because A equals B plus C plus D plus W. So in order to get W, I need to do A minus B minus C minus D. And I can just sub in now 1.75, 0.75, 0.12 minus 0.875. And so if you do the math, you get 0.005 inch. Okay, so that's the nominal. Now we also need to estimate the deviation. So what we'll do that for that is we'll estimate what the minimum W is going to be. Okay, the way we get the minimum W is when A gets its minimum value and B, C, D get their maximum value, we'll see that W will be minimum. So see if this formula makes sense to you. So A takes its minimum value. So A would be A bar, which is a mean, minus delta A. That's the minimum value for A. So it's A is going to be the shortest of its length, and then B, C, and D are going to be maximum of their length, and that's when we'll get this W. So minus B plus delta B plus C plus delta C plus D plus delta D. Okay, so if we take that difference, we should get W min. So let's sub this in. So we have 1.75 minus 0.003 minus, just give me a second, somebody on the okay, sorry about that. The problem of working from home is you got to attend to different things. Okay, so let's keep on going. So we have 0.75 plus 0.001 plus 0.12 plus 0.005, and then I'm just going to keep writing it down below, 875 plus 0.001. Okay, so just to make it clear, this is for B, this is for C, this is for D, and this thing is for A. Okay, uh, so once you sub this in, you get minus 0.005. And similarly, we need to find W max. So let's look at the figure again. Okay, so to find W max, what would the maximum of W be? It will occur when A achieves its maximum value, and B, C, D are at the minimum, sort of the opposite of what we wrote down here. So I'm going to write that down and see if this formula makes sense. W max equals, it'll be A max minus mins for the remaining stuff. So B minus delta B plus C minus delta C plus D minus delta D. So we have 1.75 plus 0.003 minus 0.75 minus 0.001 plus 0.12 minus 0.005, and finally 875 minus 0.001. Okay, so that's for B, that's for C, and this thing is for D, and of course this is for A. Okay, so doing the math here, we get 0.015. Okay, so we found the min and we found the max. So W min, as you saw, it was minus 0.005. And so we need to find now the tolerance, which is delta W. So the tolerance is going to be simply half of the max minus min, and that comes out to be half of 0.015 minus 0.005, and so that is 0.01. So if you want to write the dimensions, it would be W bar plus or minus delta W, which would be W is 0.005 plus or minus 0.01 in. So that would be our answer to part A. Okay. And so then we asked to find what is the basic value of D if W is greater than 0.003. Okay, so we want to find D when we're given some information about W. Let's do that. So in this case, W has to be greater than 0.003. And we're told that the minimum allowable value is 0.003. So W min is been specified. And so if you want to find, if you want to solve, in this case, you have to solve for D. When they say basic value, they mean what is D bar. Okay, so we can work. I'll think of this backwards. So let's first ask ourselves, what do we know about W given? How is D bar related to W? And that formula was right here in the beginning. I wrote down a formula for the mean, so we know that this is true. Okay, so I'm going to write this formula, but the difference is I'm going to move D bar to the left side and move W to the right side, and that will give me how D bar related to W bar. And once I get W bar, I'll see how to relate that to W min, and that's how I'll solve this. So let's write the formula for D bar. It is D bar equals A bar minus B bar minus C bar minus W bar. Okay, and so if we can figure out W bar, then we can write D bar. So the question is, how is W bar related to W min? Well, W min is nothing but the the nominal width minus the bilateral tolerance minus W. Right? So W min is 0.003. The nominal is unknown, and delta W is, we just computed, it's 0.01. So from that, we can solve for W bar, it's 0.013. And then we can, let me write this as 1 and 2. So then we can put 2 in 1, and we can solve for D bar. So D bar is A bar, which is 1.75 minus B bar, which is minus 0.75 minus 0.12 for C bar, and W bar we just found out it's 0.013. So D bar, or the nominal size for D, is 0.867 inch. A calculator. Okay, so when we talk about units, there are some things which are the base units, and these are typically, they are in SI system, they are for mass, for length, and for time. Actually, should write this as capital M, capital L, and D. And so once you have the base units, you can figure out the units of anything else using these base units. So these are typically the derived units. That is, you derive the units of other things based on the base units. So for example, force. Okay, so if you want to find force, we know that force is, and you can find any example of force. So force is mass times gravity. For in some other application, it could be force times what else? Just find a definition of force. So in this case, I just found mg, any definition of force, because once you have the definition, you can then try to write the units. So it's good to have units of m is mass, gravity is meters per second square, right? So it would be length times 10 raised to -2. Okay, and so that is the units of force in terms of the base units: mass, length, and time. Now you could also have, you could define different base units. Okay, you're not stuck with these MLT. You could define base units as force, F, length, and time. Okay, so I've replaced mass with force, and I can now derive units for other things based on this base unit. So an example would be, what's the unit of mass? Okay, again, find a definition for mass, and the best definition is force divided by gravity. And so we have units for force. Now, base units for force are F, for gravity is length divided by time squared, so T -2. And so now the units for mass in this new system of base units is going to be force L inverse T squared. So this is just showing you different ways in which you can go about having units. Now, there are, however, 3 main units we'll be talking about in this class. They are the SI units. So it's called the International System of Units, or the SI units. This is also known as the metric system. Okay, it's not very popular in the US. It's more popular outside the US. The base units in this case are for mass. There's mass with units of kg. For length, we have meters, and time, we have seconds. So these are the base units, M, L, and T, and we use kg, meters, and second for those things. So then you can find derived units based on that, right? Um, the one which is very popular in the US is the British system. It's the foot pound system, also known as FPS. In this case, what we do is our base units are as follows. We have force, we have length, and time. So for force, we use lb force, it's pound force. Length, we use feet, and for time, we use seconds. Okay, and so given that, we can now derive the units of anything based on these three. And the third one, which we use sometimes in this course, kind of rarely, is the inch-pound system. I'm kind of unaware of the development of this system, but here what happens is we just replace, it's the same as British system, except that we replace length with inches instead of foot. So same as FPS, except length as units of inches. Okay, so with that, we are pretty much done with the introduction to the course. Now let's dive into the actual design part. Okay, so I don't know if you got a chance, but if you looked at the handouts, I updated the handouts for today. I have this and some other plots there. If you go to Blackboard handouts, and you should see this. So this is basically the next section. We are in going to talk about material strength and stiffness here. So this is 2.1, material strength and stiffness. Okay, so this is what I'm showing you here is a specimen which is going to be tested in loading to failure. So what happens is you put this in what is known as an Instron machine. It's actually, it's usually held in the vertical direction. I'm just showing it horizontally. So it's clamped on one end, and then a force P is applied on the other end. And the reason why this force is the same as the force on the right side is because, by Newton's laws, the force on the other side should be the same as that of the force which is applied. So there's this. So let me just put this things here which are in the figure. So P is the external load on the machine. This specimen is specifically machined to be of the shape and size as shown. So L0 is the gauge length. D0 is the diameter. And what is done is, the reason why this diameter is actually smaller than the diameter of this part is because we know that stress, let me just write the stress, is force divided by area. And in this case, the area is the cross-section area. So pi d square divided by 4. Or if you want, you can simplify this as 4p divided by pi d square. Okay, so what you notice here is from the formula is that if d is, the smaller the d is, the bigger the stress is. So in other words, sigma is inversely proportional to diameter, right? And so the reason why this diameter is smaller is because the stress in this part is going to be greater than the stress in this part. Okay? And because the stress over here is greater, this part is going to fail before this part. And the reason why you want this part to fail is because here you're clamping the material, the specimen, and if it breaks here, it just ruins your test. So that's why they machine this to a smaller diameter. But this is something useful, which is, remember that stress is inversely proportional to the diameter. And that's why if you go back to the previous class, if you look at when we designed these, it's a good segue here. Let's just go to what I talked in the last class. If you remember this problem I solved, you remember we had come with a dimension of 112, and then we had two options. We could choose 110, 100 mm and 120 mm, and we chose 120 mm. We chose 120 mm because the bigger the diameter, the smaller is the stress, and that's why this actually helps us to find get the factor of safety equal or greater than the design factor. Okay, it's because of this fact. So because of this fact, the factor of safety is always greater than equal to ND. Okay, so that's for an aside. Okay, so let's moving on to this. What happens is when you apply a force P, this specimen invariably starts lengthening. Okay, which means that this length will increase, right? So then there is a term called strain. So L is the extension, the length during loading. And then let's define a quantity called strain, which you might have heard before. The strain is defined as the change in length divided by the original length. And the original length in this case is actually the gauge length, which is the length on that of the specimen. And so the change in length is the length during loading minus the original length divided by L0. So that is the strain. And this is the stress. So what's happening here is this P is increased. As P increases, L increases. And then you can basically note the stress, which is P divided by A. So you can see that as P increases, stress increases. The strain, which is L minus L0 divided by L0, will also increase because L is now increasing. And so what we do is we make a plot of the stress versus strain. So this is the stress, this is the strain, L minus L0 divided by L0. And this is actually for a material which we call ductile. So an example would be steel. So for steel, if you keep increasing the load P, you will see a stress strain curve, which looks like this. Okay, the black line is the stress strain curve, the black solid line. Okay. Now in this plot, there are a few interesting things in the plot, and I'll mention them. And these are the things which will be very important later on when we talk about design. Okay, so the points which we'll be talking about are actually PL, EL, Y, U, and F. These things. So let's define them. PL. PL is also known as the proportional limit. Okay, so what happens is when you keep increasing the stress, the curve is almost a straight line till PL. Okay, so this is the limit up till which the stress strain curve is linear. Okay, now as you further increase the stress from PL to EL, the stress strain curve starts becoming nonlinear. So 2 is EL, which is known as the elastic limit. And this is the point at which So from PL to EL, we have a non-linear response. However, beyond EL, if you keep increasing the stress beyond EL and you let go the force, you'll see that the material will not spring back to its original length. It will actually be permanently deformed. Okay, so EL is that point at which the material is within its elastic limit, and that's why it's called elastic limit. So beyond elastic limit, the material becomes plastic and does not return to L0. Okay, so if you want something to be elastic, you want to be ensure that the stress is not beyond stress at EL. Okay, so then if you keep increasing the stress beyond EL, you'll see that the curve is non-linear, and there's a point called Y where after which the stress actually starts increasing slower than the strain. So you saw this curve, it was approximately like say this way. Then beyond Y, it started to bend a little bit to the right, such that the curve has a slope which is smaller than the slope previously. So the strain increases faster than the stress. Slope decreases. So let's write that down. So Y is the yield point. So all you need to check is the change in slope. So here strain increases faster than that at the elastic limit. Okay, the stress at point Y is called the yield strength. Stress at Y is called yield strength, and it's denoted by SY. Okay, SY is one of the most important things in this course. It will come again and again when we design materials. Now, the issue here is that though it looks nice and it's very clear, it's in this figure with this markings, right? I put the PL, EL, and so on. It turns out that it's less obvious what that point EY is, because it's very difficult to distinguish this data, this curve from this curve, especially when you're doing a testing where it may not be actually linear. So what people do is they have a method called an offset method to estimate this point Y, and I'm going to describe that and next. Okay, so it is often hard to figure out the point Y. So hence, a method called an offset method is used. Okay, so what the offset method does is as following. Okay, so that's it. This is the strain. This is the stress. What is done is we find a point A, and we fix this. What this point A is going to be. It's typically chosen to be 0.2% strain, which is equal to 0.002. Right? So 0.2%, you have to multiply by 100 to get the actual length. Okay, and from here we draw a line. It's a bad line. Again. Okay, and this line has a slope equal to what is known as the Young's modulus, which is the ratio of stress to strain in the elastic limit. So the slope is E. Okay, and then assuming that you've done this experiment and you get some curve like this. Experimental curve, right? Okay, so this point is identified as the yield point. Okay, so this is purely by this method called the offset method, where the steps, and I'll write down the steps in a bit. So you start with A, assume some value, 0.2%, and this is, as I said, it's empirical. Other values people use is 0.01%. They also sometimes use 0.1%, and sometimes use 0.5%. Okay, so these are, as I say, these are just depends on what you want to use. Some people have different ways of using them. So once you have A, then you draw a line with slope E. So this is step, it's called the step 1. This is step 2. And then this point, wherever it intersects the experimental curve, is the point where you get the yield strength. This is actually the yield strength. So let me write this algorithm down neatly. So offset method to find or to compute SY. So first step is choose point A to be at 0.2% strain. That's the first step. Second, draw a line from A, let's call this A like this, with a slope of E, and then the point of intersection of the line with the experimental curve gives the yield strength. Okay, so that's how you get the yield strength. Okay, so let's then go back to this curve, and we've defined Y, and we've also shown you how to experimentally compute that. Then we have this point U called the ultimate strength, or the maximum strength of the material. It's the maximum strength the material can bear before it starts going down. So next, fourth one is U. It's the ultimate or maximum strength point. Here the stress is SU. And this is actually kind of easy to find because you see that the curve is dipping down, and that's where the SU is. So it's not too hard to get that point. After that, we have, if you go back, there's F, which is the fracture point. This is where the material breaks down. So F is the fracture. And then you'll definitely know what that point is because the material here just breaks. Material breaks. Okay, so that is the curve for a material like steel, which is ductile. If you do this to a brittle material, however, the curve looks very different. This is a curve for a brittle material. We have, it starts off nicely, linearly, but then there is the yield point, and then there is no real maximum strength point, in fact, it fails the same times the maximum strength is achieved. So at U, the material breaks. So U and F are the same for brittle materials. So the problem with brittle materials is that since they break immediately after they reach the ultimate strength, if you design something with brittle materials, they will not show any signs of deterioration. They'll just break down. That is different from ductile materials, where they will actually show some signs of failure, because here you'll see that the strength is maximum, and then you'll see that the stress decreasing, and that is a sign to tell you that something bad is going to happen, and then you might want to swap it out or strengthen the material and so on. So in general, you want to avoid brittle materials in design, because they really don't give you any signs of failure. They just fail. Okay, looks like I've a few more minutes. Let me just define one more thing and I'll be done. So there is something called the true stress strain curve. Okay, so this is actually the true strain. Okay, the stress here is the same as what we have. It's basically force divided by, or P divided by E, but the strain is computed slightly differently. The strain is, the definition of strain is the change in length divided by L, right? And so when we wrote down the strain, we just wrote delta L is L minus L0, but a better way to compute the strain is to actually treat this as dl, which is a small element. And then if you remember calculus, if you want to find the strain, you just integrate that from the length L0 at which it starts to the new length L. And if you remember, the integral of dl divided by L is natural log of L, and then you need to put the upper and lower limits. So this comes out to be natural log of L divided by L0. And that's pretty much what is plotted here. It's log L divided by L0. And so this is known as the true strain. Sorry, true strain. And it's called true strain because it uses the correct definition for strain. It uses dl divided by L and integrates that, doesn't do the approximation we talked about, L minus L0. Now, if you so by the way, you don't need new data to make this plot. You can use the data from the previous plot to make this plot, except that you'll replace the strain with this quantity. You know L and you know L0, so you can pretty much do this plot. Now, something interesting goes on here. When you do this plot, you will see that U is there and S is up there. Okay. Now, look at this and compare it with ductile materials. U is up there, but F is down there. Okay, but this is using the same data. This plot comes from the same data as before. Just that we are changing the way we are defining strain makes this different. So now U is below F. So that's the interesting thing about using the true strain. When using true strain, sigma F is greater than sigma U using true strain. However, if you use the normal strain, it's also known as the engineering strain, we see that SF is less than SU using L minus L0 divided by L0, also known as engineering strain.